Welcome, everyone. I'm excited to kick off today's presentation. Today, we'll be exploring Boolean algebra and its laws. This is a fundamental topic in digital logic and computer science. Over the next few slides, we'll dive into the key concepts, the main laws, and how they apply in real-world scenarios. So, let's get started and discover the essentials of Boolean algebra together. Let's take a closer look at what we'll cover in this section. First, we'll explore what Boolean algebra actually is. Then, we'll move on to the laws of Boolean algebra, which are fundamental rules that govern how the algebra works. Finally, we'll discuss the rules of Boolean algebra, which are the specific principles used to manipulate and simplify Boolean expressions. These concepts are essential because they form the foundation for understanding digital logic design and how computers process information. Throughout this presentation, I want you to see how these key points connect and support the overall theme of understanding logic systems in digital electronics. So let's talk about what Boolean algebra actually is. Essentially, it's a branch of mathematics that focuses on operations involving logical values, specifically using binary variables. Its main purpose is to analyze and simplify digital logic circuits, which are fundamental to how computers and electronic devices operate. Boolean algebra works with just two numbers, 0 and 1. These are the core building blocks. Think of them as representing false and true, respectively. Sometimes it's also called binary algebra or logical algebra because of this binary nature. It's interesting to note that Boolean algebra was invented by George Boole in 1854. Which shows how long this concept has been around and how vital it has become in modern computing. One key point to remember is that Boolean algebra deals exclusively with binary variables, values of 0 and 1. These variables can have simple meanings, like true or false, but they can also be interpreted in more complex ways, such as in set theory. Overall, Boolean algebra forms the foundation for digital logic design, connecting directly to how we build and understand digital systems today. Let's talk about the commutative law in Boolean algebra. This law essentially tells us that the order in which we use variables doesn't matter. No matter how we arrange the variables in an expression, the result stays the same. Think about the OR operation, which is quite similar to addition. The diagram on the slide shows an OR gate, and you can see that swapping the inputs doesn't change the output. So, for any two variables, a and b, the law states that a plus b is the same as b plus a. Similarly, for multiplication, or the AND operation, the order also doesn't matter. So, a times b is equal to b times a. This property is fundamental because it simplifies how we manipulate logical expressions and helps us understand the flexibility we have when designing digital circuits. Connecting this to the overall theme, the commutative law highlights the symmetry in Boolean algebra, making it easier to analyze and optimize logic functions. It's a key building block in understanding how logical operations work in digital systems. Let's talk about the associative law. This law tells us that when the variables involved have the same priority, the operation can be performed in any order without changing the result. For example, since multiplication and division both have the same priority, we can change their grouping freely. In the diagram shown here, we see the associative law applied to a two-input OR gate. Now, for three variables, there are specific forms of the associative law. In addition, it looks like this. A plus b plus c, but with parentheses, can be grouped as a plus b plus c, or as a plus b plus c. The key point here is that the grouping doesn't affect the overall sum. Similarly, for multiplication, when we have three variables, the law states that a times b times c can be grouped as a times b times c, or as a times b times c again. The grouping doesn't change the product. This law is particularly useful because it gives us flexibility in how we simplify and manipulate logical expressions, which ties directly into our overall theme of understanding how to optimize logic circuits efficiently. Let's talk about the distributive law. Essentially, this law explains how we can simplify complex logical expressions by distributing operations across variables. When we perform an OR operation on two or more variables, and then AND that result with a single variable, it's equivalent to first ANDing that single variable with each of the variables involved, and then ORing those results together. This process is very useful because it helps us factor expressions, making them easier to analyze and implement. For example, with three variables, the law is written as a times b plus c equals ob plus ac. In terms of overall logic design, understanding this law allows us to manipulate and simplify Boolean expressions efficiently, which is crucial for creating optimized digital circuits. It shows us how to break down complex expressions into simpler, more manageable parts. Let's take a closer look at De Morgan's theorem, which is fundamental in Boolean algebra. There are two main rules, or theorems, that help us simplify complex logic expressions. The first theorem states that if you take the complement of an AND operation, it's equivalent to the OR operation of the individual complements. In other words, the complement of a AND B equals a prime OR B prime. This shows that the complement of an AND gate functions like a NAND gate, which is a negative OR function. It's a powerful concept because it allows us to transform AND gates into OR gates with inverted inputs, or vice versa. Moving on to the second theorem, it tells us that the complement of an OR operation is the same as the AND operation of the individual complements. So, the complement of a ORB equals a prime AND B prime. This makes it equivalent to a NOR gate, which is a negative AND function. These rules are crucial because they give us a systematic way to simplify and manipulate logic circuits, connecting back to our overall goal of understanding how to optimize digital designs. By mastering De Morgan's theorems, we can switch between different logic forms easily, improving both efficiency and clarity in circuit design. Now, let's take a closer look at the rules of Boolean algebra. These rules are fundamental because they allow us to simplify and manipulate logical expressions efficiently. First, we have the identity laws, which tell us that any variable AND'd with 1 stays the same, and any variable OR'd with 0 also remains unchanged. This is quite intuitive. Think of 1 as a neutral element for AND, and 0 as a neutral element for OR. Next, the null laws state that any variable AND'd with 0 results in 0, and OR'd with 1 results in 1, which highlights how these values dominate the expressions. The complement laws are also crucial. They state that a variable AND'd with its complement gives 0, and OR'd with its complement gives 1. These are the foundation for simplifying expressions and understanding the relationships between variables. Lastly, the distributive laws provide us with rules for expanding or factoring expressions, much like in regular algebra. Together, these rules form the backbone of Boolean algebra, enabling us to design and optimize digital circuits effectively. Remember, mastering these rules helps us move from complex logic to simpler, more efficient solutions.